In this video, we'll continue our discussion on polynomial functions and their graphs. So we'll begin first with a quick review of what a polynomial function is. We'll go through end behavior just to review that, because ultimately building up to being able to look at a single polynomial function and graph it just on our knowledge and understanding of the function. Then we'll talk about zeros of polynomials, the shape of polynomials near zeros, and local maxima and minima. So first, recall that a polynomial function of degree n looks like this. an minus 1, a1, a0, and all of the numbers in between in front of variables, those are the coefficients of the polynomial. a0 is the constant coefficient, or the constant term. an here, that's the leading coefficient, and an x to the n is the leading term. Recall also that the end behavior of polynomials is defined as follows. The end behavior for some polynomial that looks like this is determined by its degree, n, and the sign of the leading coefficient, an. I'm not going to talk through all of this since we've already been through it, but just a quick refresher. So let's take a look at this graph. First, I thought it might be useful to talk about the end behavior. So if we look as x gets really negative, the graph gets really negative. So we could say that y goes to negative infinity as x goes to negative infinity, and y goes to negative infinity as x goes to positive infinity. Now, this should actually tell us something. This should tell us that both the leading coefficient an is negative and that the degree n is even. And it turns out that this is a kind of typical x to the fourth kind of graph. I don't know exactly what the polynomial looks like, but it's something like x to the fourth. Now I want to draw our attention to these spots here, just to begin with. So we might call these the x-intercepts, right? We know that here, here, and here are when the graph p, the polynomial p of x, so the graph p crosses the x-axis there. So we call these x-intercepts. Let me just give this one a name. We'll give that one a name, c. So we might call c an x-intercept. And we know that we can algebraically describe that as when p of x equals 0. We also know from our discussion of quadratics that, for example, if we had something like p of x equals, x squared minus x, that we can find the x-intercepts by factoring. So this factors into x minus 0 and x minus 1. So this particular quadratic polynomial has intercepts at x equals 0 and x equals 1. And so these are the factors, right? So the x-intercepts, in other words, the solutions to the equation p of x equals 0, also are called factors. We also have another name for these. We can call those zeros. So these are four equivalent definitions of what's happening at some c when the polynomial p of x crosses the x-axis. Now, another thing that I want to notice with this graph is if I zoom in a little bit, I'm going to zoom in right here on this spot, and I'm going to erase this. So what I want to notice here is that when we hit that, we'll call that another c, when we cross the x-axis, what's happening to the polynomial p of x? The sign is changing, right? If we're just to the left of c, we'll call that a, and if we're just to the right of c, we'll call that b. P of a is positive, p of b is negative. And that tells us that we've crossed the x-axis. We can't have crossed the x-axis without also having changed sign. So whenever the polynomial p of x changes sign, we should also know that we have a 0. And we can summarize that right down here. So we've got two definitions. The real zeros of polynomials. If p is a polynomial and c is a real number, then the following are equivalent. So c is just that point where the polynomial crosses the x-axis. We said that we could call c a zero of p. X equals c is a solution to the equation p of x equals 0, kind of typically how we would find the x-intercepts. X minus c is a factor of p, kind of a byproduct and related to number 2. And 4, c is an intercept of the graph of p, right? X-intercept. The second thing we talked about is what's called the intermediate value theorem for polynomials. If p is a polynomial and p of a and p of b have opposite signs, then there exists at least one value c between a and b for which p of c equals 0. In other words, if we change sign at some point, if we have two x values for which the first one is positive and the second one is negative, then we know that we've crossed the x-axis, and therefore there must be at least one 0. Of course, if we had a and b really far apart, then we might have a chance that we've crossed the x-axis more than once. But as long as we know that we've changed sign, then we know that we've crossed the x-axis, and therefore we have a 0. So I have two more graphs here for you, and I want to kind of develop an intuition about what might be going on here. So looking at this c, so looking at that c, in this case we know that c equals 0, and looking at this c, I want to notice what's going on close to those zeros. So we'll call this first one f, a polynomial f, and we'll call the second one a polynomial g. If we zoom in, just right here, what kind of graph does this look like around the 0c? I think to me that looks like an x squared, right? Like this behavior kind of looks like x squared. Just, something to notice. And then switching over to G, similar kind of pattern identifying. If we look at the behavior around this C, the 0 for one of the zeros for G, this behavior looks like that kind of looks like an x cubed, right? Or something like. All right, so we'll put that in our back pocket. And kind of broadly, what's happening here at these two instances, where in F we're saying that the behavior around that C looks like x squared, and in G the behavior around the 0 for G that we have looks like x cubed. What's happening there is that we have copies of that 0 in the fully factored form of both F and G. So just for instance, this is not exactly the same graph, but F might look something like this, x squared, and we might have, I don't know, an x minus 2 and an x plus 2. Yeah, we could call that negative 2 and 2. But the point being is that when we look at the equation of f, we actually have a copy of x. This is called multiplicity. So in this case, the 0, 0 has multiplicity 2. And similarly, in the graph of G, that 0 at C might have multiplicity 3. What I'm trying to get you to see is that the multiplicity, the number of copies of a certain 0 we have, kind of determines the behavior around that 0. So in both F and G, these both look like an even degree polynomial, right? And we know that because of the end behavior, right? Since the graph goes in the same direction as x goes to negative infinity as it does to positive infinity, we know that there's even degree. And in each case, we have a different number of local maxima or minima. But we are limited by the degree of the polynomial. So for example, if f is the degree of a polynomial of degree 4, we might notice that at most we have 3, 1, 2, 3 local minima and maxima. So I'll summarize these two concepts. The shape of the graph near a zero of multiplicity m. So remember, zeros are when a polynomial crosses the x-axis, and a zero is of multiplicity m when there are many, or there's more than one copies of that zero in the equation of the polynomial. If c is a zero, p of multiplicity m, then the shape of the graph of p near that zero c is as follows. If the multiplicity of c is odd and greater than 1, then the shape of the graph near that x-intercept c will be looking kind of cubic, or some odd power. And if the multiplicity of c is even for m greater than 1, will kind of look like a polynomial of even power around that zero c. And local extreme of polynomials: if p of x is a polynomial of degree n, then the graph of p has at most n minus 1 extrema. So in this video, we've actually covered quite a bit. All we've looked at really is that x-intercepts can also be called zeros, and that's a useful kind of formal definition for what's happening algebraically, graphically at those points. We know that if we have an a and a b, and p of a and p of b are different signs, then there must be a zero in between, at least one zero in between p of a and p of b. The shape of the graph near a zero multiplicity m, and then kind of last but not least, the local extreme of polynomials. We said that we could have at most n minus 1 local extrema. So I'll be sure to post up an example video so you can see how to piece all of this together.